So let me pull this up. Let's just write down the information from this slide. So we have HCl, we have the melting point, and the boiling point. Boiling. 114.8. And that is it negative? No. Negative 85. Is that right? Oh, they're both negative. Okay, melting, boiling, and then the ones we're looking at are negative 145, negative 103, and negative 31 Celsius. Okay, so let's just make this big. Oh, let's try it. Okay, so we have these three temperatures. So, if we have hydrochloric acid and it's at negative 145, what would the phase be? So I think this is tricky when it's negative. So what I like to do is I like to say, okay, if it's below negative 114, and then it's frozen, so then it's going to be solid. So if it's going to be less than that, then it's going to be solid. Okay. If it's between negative 85 and negative 114, then it's going to be a liquid, right? Because between boiling and melting into boiling is liquid. And then if it's above negative 85, so if it's bigger than negative 85, then it's going to be a gas. So this helps me, especially when they're the negative ones. The negative ones throw me off. So I like to draw on kind of like a number line. So these are the low temperature, and then these are higher temperatures. Okay, so I think I heard it. This one should be a solid, right? So the picture options, we have to decide. So we have hydrochloric acid. So we need to look for something where hydrogen and chlorine are bonded together. So we need something like this where they're a solid. So it needs to be really organized. Okay, and they're bonded. They have to be bonded together. The atoms can't be separated. Okay. So make sure you're looking for something they're very organized, the atoms are bonded together, and you have just two types of atoms, a hydrogen and a chlorine. Okay, how about this one, 103, where would that fit? That would be between melting and boiling, so it's melted, so it's a liquid, yep. So then we're looking for something where the hydrogen chloride is kind of like sliding past each other, but they're still pretty close together. And we have a molecule like we had in the solid. That we can't have something where they're broken apart. Okay, that's not hydrogen chloride anymore. So something that they're just like the molecules just slide past each other. And then this one would be past the boiling point, so that would be a gas. Good, the gas phase. So we still have molecules, they haven't broken apart. So somehow they need to be bonded together. And then they need to be further apart than the liquid. Okay. All right. Do you think you can do that on the final? You feel pretty good? Okay. I think the biggest thing that people miss on this is they try to pick when the atoms are like separate from each other. If it's HCl, that's a molecule. They need to be bonded. Okay. And then the part that tricks me, which doesn't trick as many of you, is that the bigger negative number is smaller. That's confusing to me. So, okay, let's go. How are you doing on lab 4? Do you need to go over another one of the equations? Okay, let's do another one of those. They're kind of tricky. I think that you guys can do it, so I don't think we'll go over all of them, but hello. Oh, no, you're okay. Thank you. Thank you. I have to catch it or I'd be missed. Okay, so let's pick one more to do. So we have 2, 3, or 4. Is there one in particular? 3 or 4? Does anyone else have a preference besides 3 or 4? Or like out of 3 or 4? Which one do you want to do?
The harder one.
The harder one is number 2. But you already did number 2? I think 2 is the hardest one for me.
Let's do 2. Yeah, let's do 2.
Wesley's already done number 2.
Well, we can make sure that he's right.
I guess we'll do 2.
Yeah.
Are you okay with trying 2?
At least I'll know if I did it.
Okay, okay.
We can do it and then we do another one.
True. That's a great idea.
Okay, let's pull up the. That's what I think. Let me check. I thought that 2 is pretty tricky for me.
Yeah, I think that's true.
It has extra, yeah. Okay, number 4. I will just tell you, number 4 has 2 precipitates.
Oh no.
Yes, I said that right. 2 solids. So number 4, right down there's 2 solids for number 4. But it's not hard. I think number 2 is tricky. So we are going to go through this. Hopefully you've done this part, right? You do the description. So then we're going to look at our information. It says aluminum sulfate is added to sodium carbonate and water to produce aluminum hydroxide, sodium sulfate, and carbon dioxide. And I think that's why this one's the trickiest, is because it has so many things going on. Okay, so let's write out what we have. So I'm going to make a box for like showing my work, and then I'm going to write my equation. So this one, we have aluminum and sulfate. So aluminum is always a +3 charge. Okay, so I know that because the first column is +1 if it's a metal. The second one is a +2 charge. Aluminum, we skip the transition metals. Aluminum is in the third kind of column. That column, most of them form +3. So aluminum is one of our transition metal or post-transition metal exceptions that always forms the same charge. So we can just memorize that aluminum is 3+. Okay, and then we have sulfate. Sulfate's an ion that we were supposed to memorize. So sulfate is SO4 2-. Does that sound familiar from chapter 3? Okay, and then I have to charge balance. This is an ionic compound, so I need the same charges to balance. So the way I do this is I do the crisscross method. I take this 3+ and I move it down. So I need 3 sulfates to balance 2 aluminums. I'm bringing the charge down. So then my first thing is aluminum sulfate, and aluminum sulfate has 2 aluminums and SO4. I have 3 SO4s. 2 aluminums, 3 SO4s.
How would one say that?
Aluminum sulfates.
Aluminum
Oh,
sulfate, so you
yeah.
wouldn't say like AL?
Nope, because I know I can figure out how many there are by charge balancing for ionic compounds.
Only ever say aluminum sulfate like that.
Yes, right. Because aluminum is always +3. So almost any other transition metal, you have to say the charge because it's not always the same.
But if you were to say something in parentheses and there's an iteration of it, so hydroxide, and there's an iteration, or sulfate is an iteration, so SO4, would you say SO4 3 or something like that? Or?
No, just aluminum sulfate or aluminum hydroxide.
Cool.
Yeah. Okay. Yes. Okay, the next piece of this is added to sodium carbonate. Do you know the charge on sodium?
-2. No.
Not a minus. +1. Positive. Yep. It's in the first column. Everything in the first column forms a +1. Okay, the next piece of this is sodium carbonate. Do you remember the formula for carbonate? CO3 2-. That's carbonate. Okay. And then we can do the crisscross. We need 1 carbonate ion. Oops, I put a 2. I don't know why I put a 2. 1 carbonate for 2 sodiums. So then that charge balances. I have 2 plus charges for 2 minus charges. So then my next piece is Na2CO3. So I have 2 sodiums, 1 carbonate. Okay, the next piece says water. So just add water. Usually we don't write water in the equation. We are writing it here because it's participating. It's doing something. It's reacting. Okay, if it doesn't react, then it's just a solvent. We don't write solvents in the chemical equation unless they are reacting. And then it says to produce. So I'm going to put my arrow. Aluminum hydroxide. So I know aluminum, we just talked about that. That's a 3 plus charge. What's the charge on hydroxide? Just 1 minus. Yep. Hydroxide OH is just 1 minus. So then I need 3 hydroxides to balance 1 aluminum. So AlOH3. That's my aluminum hydroxide. Okay, right now I don't have the phases, so I'm going to go back and put the phases. I'm not there yet. And what else we have? Produce aluminum hydroxide, sodium sulfate. I'm running out of show my workspace. Sodium we just said was plus charge. Sulfate was SO4 2 minus. Okay, so then I need 2 sodiums for 1 sulfate. Na 2 sodiums for 1 SO4. And we have carbon dioxide. When you guys did this, did it bubble?
Yeah.
Oh, good. That's great. Okay, that's because we have CO2. It says that we made CO2, which is a gas. Okay, so let's go back through and label all the rest of the phases. Aluminum sulfate was something that we started with. So if we started with it, it's aqueous. Yeah, it's dissolved in water, AQ. If you need to shove them in there somewhere, that's fine. NaCO2 is also aqueous because that's what we started with. Water is not aqueous. That doesn't make sense to say water dissolved in water. It's just a liquid.
Yeah.
And then we have to decide these 2 things. We have to decide if they are solid or aqueous. So we need to look at the chart. This one has aluminum, which is not on the chart that I gave you last time. So that's annoying. So let me find the chart. So I'm going to go through the Weaver State canvas. I'm looking for, I looked for the wrong class. I'm looking for the module, CRT module, lab 4. We're still looking up. And then let's go to instruction. So we're looking for this chart thing that includes aluminum. That's what we need. Great. So we're going to scroll down. Here's our chart. Aluminum's right on the top. I don't know why all the ends. So then I have to go through and see. So we have what? We have aluminum hydroxide. So aluminum hydroxide, that's going to be a solid. So if we form a solid, that's going to be our solid. Then we also have to check aluminum. What was the other one? Sulfate. Aluminum sulfate says it's aqueous, so that's soluble. So we just need to spell aluminum hydroxide as our solid and aluminum sulfate. Oh, we got it. That's right there. Okay, sodium, and then which one's sulfate? 1, 2, 3. 1, 2, 3, 1, 2. So that's also really solid.
3.
Okay. Okay, so then we need to label those. The other thing we need to do is we need to balance this. This is not balanced. Okay, so we said this one is a solid. So that tells us what needs to go in this box. Formula of precipitate. That is this one. This is our precipitate solid. This one was aqueous, AQ. So formula of precipitate. This is like our balance equation, but it's not balanced yet. So we just need to kind of play around with this. We need 2 aluminum, so I'm just going to put 2 here. 2 aluminums, 2 aluminums. Let's see. I'm going to balance sulfate as an ion because this should work out. Sometimes it doesn't, but this one should work out. So we got 3 sulfates here. I'm going to put a 3 here. Now I have 3 sulfates, 3 sulfates. I also have 6 sodium, so I'm going to put a 3 here. That's going to give me 6 sodium, 6 sodiums. That kind of messed up my carbons, so I'm going to put a 3 here. I just kind of blindly doing this. So we've got 3 carbons. This gives me 9 oxygens that aren't part of sulfate plus 1, so that's 10. Over here we have 6, and we have 3 times oxygen times 2, that's 6. So we got 12 over here. Other thing we have is 3 hydrogens here. So I'm going to put a 3. Oh, that's 6. 3 times 2, that's 6. So I'm going to put a 3 here. So that gives me now I have 6 hydrogens, 6 hydrogens, 12 oxygens, and then if I go over here, and this is not with sulfate. So sulfate, I've got 3 sulfate. Oops, let me skew that up a little bit. We have 3 sulfates over here, and we have 3 sulfates. So let's see, this oxygen that's not in sulfate, we have 9 plus 3 is 12. So we also have 12 oxygens. I should put this the other way. So now it's balanced. So I needed a nothing here, a 3, a 3, a 2, a 3, a 3. And that's simplified also. You want to make sure that you can't divide a 3 out of all of them or a 2 out of all of them, all of the coefficients. Okay, so now we have our balanced chemical equation. So the next part is the net, or total ionic. Total ionic. Do you remember what to do for the total ionic equation? So maybe look back at part number 1. What did we do?
Oh, you leave out or you left out.
So that we're doing that. So complete ionic. Okay, so we are going to break anything apart into its ion, if it can form an ion. Yes. So we know it can form an ion if it's in the aqueous form, then it's going to form its ion. So this one here can break into its ions because it's aqueous. So this ion, we have 2 aluminum 3 pluses. That's aqueous. Oops, AQ. My pen is not very a fine pen, so it's hard to see. This one is SO4 2 minus, and we got 3 of those. So I'm going to do plus 3 SO4 2 minus. That's aqueous. Okay, this gets kind of messy and long, so I think I might do one side and then the next side. Okay, the next one, I have 3 times 2, that's 6. I have 6 sodiums, 6 Na pluses. This is aqueous, so it can break into its ions, and that's aqueous. Plus, we got 3 carbonates. So this 3, I'm saying I have 3 carbonates. CO3 2 minus, that's going to break into its ions, and that's aqueous. And water is liquid. Water does not break into ions. It's covalent. So you still got 3 waters. That's a liquid. Okay, I'm going to put my arrow here. So this is my reactants. This next line is going to be my products. So this one's solid. If it's solid, it won't break into its ions. That's why it's precipitating. It doesn't dissolve. It's solid. It's a precipitate. So I'm just going to write that. 2Al OH. I got 3 hydroxides in there. That's going to be our solid. Okay. And then we have this one. This one's aqueous. Aluminum sulfate. Or not aluminum. Sodium sulfate. So we can put this as its ions. We got 6 NAs. 6 Na pluses. That's aqueous. We got 3 sulfates. Oh, I don't know why I'm going to put 8. 3 SO4, 2 minuses. Those are aqueous. And we have this last thing. We have 3 carbon dioxides, which are gas in the gas phase. Okay, so then we look through here. Is there anything on my reactant side, which is my top of my reaction, and also in the reactants? Is there anything that matches? Okay, sodium, I see these 2. Anything else that's matching? It looks like these 3 sulfates. These are the same. So then when I write my net ionic equation, these ones aren't doing anything. These are called our what is it called? Spectator ions. They're not participating. They're just spectating. So we're not going to put them in the net ionic equation. So the last part, we're going to write everything but not our spectator ions. So this will be 2Al3+. That's aqueous. We don't write this because it's on both sides. It doesn't really do anything. It's just hanging out. We have, oh, yes. Thank you. Thanks. So this one's participating. Anything that's actually reacting. Everything else is just spectating. It's just there to charge balance. It's not doing anything. Plus 3 waters. The water reacted here goes to, I might fit it here. This one's shorter. So 2 Al hydroxide solid. So, and our carbon dioxide. Oh, there we go. Gas. All of these should still stay balanced. I think they are balanced because we just left our coefficients, or from our balanced equation, we kept the number. So this is telling me that overall, this is what's going on. My aluminum is reacting with my carbonate and my water to form aluminum hydroxide and carbon dioxide gas. And those other things are there, but they're just not participating. They're spectator ions. Okay, questions on that? So that was number 2. I think that's the hardest one. The other ones are very similar to that. So I'm gonna let you guys do those ones. Let's do some topics in chapter 7 and then we can have some work time. Does that work? Okay. All right. Let me close this. No, I don't want to close that. I just need my Alex up here. Okay, and I'm going to go back and forth. I have our list of topics. So we talked about Boyle's law last time. I don't remember if we got to Charles' law. Do you remember? Okay, so let's start on that one. I think I have it up here. Okay, so Charles' law. I have a little reminder paper for me. So this one is like the balloon problem. We always have some kind of thing that we're doing. Okay, so this says we have an Arctic weather balloon and it's filled with 32 liters of helium inside a preparation shed. The temperature inside the shed is 6 degrees Celsius. That's kind of cold. The balloon is then taken outside where the temperature is negative 30 degrees Celsius. Calculate the new volume of the balloon. So we have to think about this. So, I have a video actually.
Wait, can we start with the interconverting temperatures in Celsius and Kelvins? Because that one's the one that you're doing is not, so we can't get to it.
Interconverting temperatures. That one is from a previous chapter.
Oh,
Do you remember that equation?
I don't.
Okay, I think I have it in my slides. Let me find my slides. Temperature.
I can look at the next one.
Okay, this is we need the temperature to be in Kelvin for this. So this is when the pressure is constant. So we're staying on Earth. We're just going from inside the building to outside the building. So the pressure is staying constant. So then we get this relationship. The volume, the initial volume over the initial temperature equals the second volume over the second temperature. For this, temperature must be in Kelvin, and that's why it's making you redo this topic if you need to do that. Hello. Yes.
Yeah,
Oh, I'm glad you remembered it. So we talked about interconverting Kelvin and Celsius. I think it was like the first chapter. It was pretty early. Anyways, oh, I moved this. So you need to make sure that you know how to do this. If you don't remember how to do this, write this on your note card. This does not show up in Alex. So I would put this on my note card for the test, so I don't forget. So Kelvin is equal to Celsius plus 273.15. The 273.15 does not count towards the sig figs. You have to look at the Celsius, and then you have to think about when you're adding and subtracting, how do we get sig figs when we're adding and subtracting? Do you remember? When we're adding and subtracting, how do we keep track of sig figs? What tells us? No, not that one. Decimal places. So if you have more decimal, like you keep the least amount of decimal places. Does that sound familiar? We don't do adding a lot, so that one that doesn't come up as much. So we keep the least amount of decimal places. Okay. All right, let's watch this person do this balloon. Oh, after an ad. Oh, wait. This guy is from Utah State. Oh, wait. Okay. I changed my sound to my computer. This is from Utah State Physics. Utah State Physics. Oh, because we're kind of in the physical chemistry section. Yes, so this is kind of chemistry overlap. Oh, yeah. Okay. So what do you think is going to happen? What is your prediction? Okay, so you think it's going to constrict? Do you think it's going to get bigger? Okay.
I'll be surprised if it doesn't.
You're going to condense? Okay, you think it's going to pop? Okay, let's see what happens. Okay, so think about what's happening. So pressure, the more the particles hit the wall, the higher the pressure. So what happens to you when you get cold? Do you feel like you're going to run around or you're going to like hold still? Okay, so the gas particles, when they get cold, they stop moving so much. So then the pressure goes down. So if the temperature goes down, the pressure will go down. The volume goes down. Okay, so less things hitting the edge. Okay. Okay. So what was that liquid? Do you remember what they called it? The liquid is helium. The liquid is liquid nitrogen. Okay, so that's what this problem is in Alex. So when you are doing this problem, imagine a balloon, the balloon problem, okay? Temperature goes down, volume goes down, okay? Pressure is the same. Okay, let's do this one together. Okay, let's go here. All right. So let's write down our initial values. So we have, let's do it like this. We got, if we do it like this, we have P, V, N, T, and then we have our initial values, our final values, and then what we expect to happen. Let's try this table. So here, pressure is staying constant because it's not changing. We're still in the atmosphere. The atmosphere is giving the balloon pressure. The volume is filled with 32.3 liters, so that's 32.3. The number of moles, this is number of moles, that's not going to change here. We're not emptying the balloon or filling the balloon after we initially fill it. So we initially fill it, and then the only thing we change is the temperature. So let's go over here. It says the temperature starts at 6 degrees, so that's our initial temperature. Okay, we need this to be in Kelvin. So first thing let's do is change that to Kelvin. So we're going to take 6 degrees Celsius. We're going to add 273.15. That's our definition of going from Celsius to Kelvin. So that's going to be 279. Do we agree with that? Just added this. And then this one only has no decimal places, so we get no decimal places, okay? And that's Kelvin. The other thing we are going to do here is this one now has 3 sig figs, okay? No decimal places, but it has 3 sig figs. This one has 1, that's true, but once we get it into Kelvin, now it has 3 sig figs. So that's how many sig figs we're gonna go with. So that's kind of weird. That's thrown me off for a while, so 279 Kelvin. Okay, and then it says we go outside and the temperature is minus 30. So let's do that. We're going to change that to Kelvin from Celsius. So 30, basically 273 minus 30. This also has no decimal places, so we should end up with 3 sig figs. Is that 240? 243? I'm going to say that's 243. Okay, so let's see. That goes here, 243 Kelvin. Okay, so think about our video. So what happens is our temperature is going down. Do you agree with that? 6 to negative 30 or 279 to 243, our temperature is going down. So what happens to our volume if the temperature is going down? It should also go down. So think about that video. The balloon's temperature goes down, the volume of the balloon went down. Okay, so what we're going to do is we need the volume. So we're going to take that number 32.3, I don't know why there's not a decimal, liters. And then we need the volume to go down. So I'm just going to make a fraction out of the temperatures and make this go down. So what needs to go on the top to make this go down? 243 needs to go on the top, Kelvin. It needs to be in Kelvin. What does this one have? That one just goes on the bottom. Okay, and so Kelvin cancels out, we'll get liters, and that's what we're looking for. Okay, so let's put that in the calculator. Oh, let's scoot it over until we have our calculator. Oh. 32.3 times 243 divided by 279. Okay, and then because all of our values have 3 sig figs, after we convert it to Kelvin, then our answer will also have 3 sig figs. So 28.1. Let's check, make sure that's right. I got it wrong last time. Okay. Does that make sense? The other way to do this is with those equations, and you'll get the same relationship that we find here. Okay. Questions? Do you want to do another one? Okay. More practice. So this one, I call this one the balloon problem. So just think about what's happening with the balloon. Okay, next one. Let me just flip it over. Oh, just kidding. Let's erase and then flip it over. Okay, Arctic weather balloons. This is the balloon problem. So P, V, N, T. Initial, final. What do you expect to happen? So again, we have an Arctic weather balloon, and it has initially 5.95 liters volume. 5.95 liters of helium gas in the shed. And then the temperature of the shed is 11. But remember, we need to convert that. It must be in Kelvin for this example, this problem. 273.15. And that's going to be, what is that? 284. And this one has no decimals, so this one has no decimals, but it has 3 sig figs. So 284. Oh, I'm putting Kelvin. And the final temperature is 2 degrees Celsius. So that will be 275 Kelvin. Also, it says the pressure stays constant at 1 atmosphere. So I'm just going to say, okay, pressure stays constant. I don't need to worry about that one. Also, I filled the balloon and it's staying full. So I'm not going to change the number of particles. The only thing I'm changing is the temperature, and then I have to see what happens to the pressure, or the volume, excuse me. So what happened to the temperature? It went down. So think back to that video. If we have a balloon and we decrease the temperature, it's at the same pressure, then our volume better shrink too. So that means we need to start with our volume, 5.95 liters. And then we need to make this number go down with these two numbers multiplied. The only way to do that is if we have a ratio of the small number on the top. Kelvins cancels out, we get liters. So 5.95 times 275 divided by 284. And then, again, everything had 3 sig figs. So after we converted to Kelvin. So remember, make sure you convert to Kelvin and then you can look at sig figs. So our volume will be 5.76. Oops, that's a 7. The other thing you need to look at here is, what do we care about? I can't remember what I was going to say. I don't remember. Okay, questions? Does that make sense? Okay. All right, check. Oh, just kind of make sure you're paying attention if it's going down or up. I think most of them, I don't know. So far, they've all been down, but they might go up too. Okay, let's see if we can find one. If it goes up, so for some reason, if this went up, then your volume would go up. Yeah, and you just put the big number on top. Yes, put the big number on top of your fraction. I think they are. Oh, this is the same. So what happens if it's the same? Whoa, the temperature inside is the same as outside. Then it should stay the same, yeah. Yeah, it says that. Okay. Does it ever go up? Oops, did this one go up? I just missed it. I don't know. It seems like they're all going down.
Well, it will go down because it's about like the topic is about like pressure going down. That's why it's the shield and the arc.
This one seems like, so you could have it the other way where your weather station inside is colder, but then it wouldn't be Arctic wind probably. Yeah. Hopefully your prep station is warmer than the Arctic. Okay, looks like it's going to go down or it might stay the same, but know what to do if for some reason it pops up as going up. Okay, so that was Charles' law. The next one I want to look at is Avogadro's law. Okay, so this problem, we're going to do the same thing that we did here with our little chart, and we'll see if our chart works. Our chart should also work here. So this one we have, this one has an equation in it. So we have methane. Also notice, it's not telling us the equation for methane. So you need to start picking up on what is methane. Do you know that? What's methane? That's ammonia. But that's another one you have to know. Methane. Methane is CH4. So that's one you're going to start having to memorize. Methane and chlorine gas. When it says chlorine gas, when I read this, what should I think? Cl2. Good. So if it's any of those dark green elements, they're going to come as a pair. Hydrogen gas, nitrogen gas, oxygen gas, chlorine gas, bromine gas, iodine gas. So when I see chlorine gas, I'm going to put Cl2, or I might get this wrong. Okay. Cl2 and, oh, yeah. Methane and chlorine gas react to form hydrogen chloride gas, HCl, and carbon tetrachloride gas. What's tetra?
3.
4. So carbon with tetrachloride, 4 chlorines. Gas. Oh, I don't have to label these. These are all gases, but I'm not going to label them because I don't have to turn my equation in. Okay, but I do have to balance this. So let's see. Let's balance it. Oops. Carbon, hydrogen, chlorine. So let's see, I've got 4 chlorines, 1 carbon, 1 hydrogen, 1 carbon, 4 hydrogens, 2 chlorines. Okay, so I need this to be 4. So I'm going to put a 4 here. Now I have 4, but I also have 8 chlorines, right? 4 and 4. Okay, so 8. So then I have to go back over here and make this have 8. So I'm going to put a 4 here. 4 times 2, that gives me 8 chlorines. So now my atoms are balanced. Okay, I have to do that because it's asking me, let's see, what volume of hydrogen chloride would be produced by this reaction if this volume of methane were consumed? So we are used to using these ratios, the mole ratio, in moles. If it's close to an ideal gas, we can also use that for volume. Okay. Let me think if we can use our table. Let's write it out and then think about it. Okay, so we've got our P, V, N, T, initial, final, what we expect to happen. I'm not sure we can use that here. I'm not sure. Let's think about it. So, does it say anything about the temperature? I don't think so. I think the only thing that's changing is our volume. So, temperature is not changing. Pressure is not changing. I think this one's just a stoichiometric problem. So, I think this one's just volume. So, we're just going to use the mole ratio. So, we are starting with 6.37 liters. And we have methane, CH4. So that's what we're starting with. Okay. It's asking what volume of hydrogen chloride? Volume of hydrogen chloride. So we're looking for liters of HCl. Okay. Oops, there we go. So then we need the ratio, the mole ratio from our chemical equation that relates HCl to methane. So which one should we put on the top? So HCl goes on the top. So 4 HCl. And then how many methanes? To how many methanes? Yeah, there's nothing here, so that's just a 1. So this one, these two are 1. So 1. Oh, and I guess we could put liter. 1 liter of methane. And then we just multiply that. Oh, come here. 6.37 times by 4. Oh, that's all. 4 over 1. Okay, 25.48. So the value they give us has 3 sig figs, so our answer should have 3. 25.5. Ah. And then they asked us for a unit, so we're going to put liters. I don't know why some of them ask us and some of them don't. Okay, so this one's just a stoichiometry problem. Okay, questions on that? Okay, do you want to do another one of those?
Is there going to be any other altered form?
Yes, I think so. Milliliters. So they have a different chemical equation and then different units, but same process. Yep. Yep. Okay, I think that's all for that one. Okay, let's do the ideal equation of state, which is also called, everyone else in the world calls it the ideal gas law. So I'm not sure why Alex calls it this. Okay, this one has lots of different versions. So let's try this type. Okay, so this one, we are just going to use the ideal equation of state. I'm not sure we can use that. Let's try. For today, let's do PV equals nRT. Okay, so we're going to write down all the things that we have. So it says a reaction at this temperature. So we have temperature, -3 Celsius, so plus 273.15. That's the thing that anytime I see temperature not in Kelvin for this chapter, almost every time I'm going to put it in Kelvin. So that's going to be 273 sig figs. Evolves, that's N. We just found N, 673 millimoles. But this is in millimoles. We would like that to be in just moles. So I'm going to convert that to just moles. So I'm going to divide by 1,000, 0.673 just moles. Are we okay so far? So same number in different units. Okay, calculate the volume of dinitrogen monoxide gas that is collected. So that was what was produced. We're looking for the volume. So this is what we're looking for. You can assume the pressure in the room is exactly 1 atmosphere. So pressure is always 1. Oops, ATM. The other thing that we need here, so we have temperature, we have number of moles, we have pressure, we need this R. Do you remember that what that was from before? That's a constant. That's called the universal gas constant. If we go to the data, the universal gas constant is always the same. I like to write it on my note card. Oh, actually, it's a fundamental constant. Oh, thank you. I could not find it. Okay, there we go. It's a fundamental constant. We are using the top one. Our answer our values need to be in liters, atmospheres, moles, Kelvin, because we are using this gas constant. So I'm going to write it down. R is going to be 0.0820574. Oh, actually, this is also on the Alex calculator. If you're not using your Alex calculator, then you'll have to remember it. Okay, those little -1, that just means it's on the bottom. Per mole per Kelvin. Okay, we got that. We need a minute. Okay, so then I'm just going to set up this so that I'm solving for volume. So if I divide all the sides by pressure, then I'll get volume. So volume is the same as number of moles times the gas constant times temperature in Kelvin divided by the pressure in atmospheres, and that will give us the volume. First, what should we expect should happen? Is anything changing? Are we going to be able to say? No, we're just calculating. We're not. Okay, never mind. Okay, so I'm going to plug in number of moles, 0.673. The gas constant is this one, 0.082057. I'm going to put in my temperature in Kelvin, has to be in Kelvin. All over pressure, which is 1 atmosphere. That one's easy. Okay, and then I can have my Alex calculator. And we have 0.673 times the gas constant. It's in my, so if you go to the pi button, it should be there. Gas constant in liter, atmosphere, mole, Kelvin. Also, this is telling you, if you can't remember, oh, what should the number of moles be in? Oh, it should be in moles. Sometimes they give you grams, so you have to convert. What should my temperature be in? Oh, it should be in Kelvin. What should my pressure be in? Oh, it should be in atmosphere. So that will help you remember, make sure your units are in the right unit. Make sure your values are in the right unit. Okay, times by 270, the temperature, divided by 1. I'm not going to divide by 1 because that won't do anything anyways. 14.9. All of the values have 3. The constant doesn't count against my sig figs. I guess it's least sig figs anyways. I guess the pressure also doesn't count against my sig figs. 14.9. Okay. All right, should we do another one of these?
Yeah,
These ones have
there's some that are asked.
all sorts of questions. Okay, this is the worst one. They told us they would take this off and they still haven't. So this one will not be on the final. This type could be on the test and it will be on your assignment, but it will not be on the final. But it is a painful one, so. All right, so it says we have a chemical engineer is trying to figure out the operating safe temperature of a high pressure gas reaction vessel. We have a stainless steel cylinder that measures. So first, we have to calculate the volume. So we're trying to find PV. Okay, PV equals nRT. That's our equation. And they're trying to tell us about the volume, but we have to calculate that. So this is annoying. So it's a cylinder. How do we find the volume of a cylinder? Do you remember?
Pi r squared times the height.
Yes, good. You got it. It is also somewhere in Alex, if you can't remember that. This actually, yeah. I don't think it's going to be, well, this could be on the test. So it's in Alex somewhere if you can't remember the equation and the data. Okay, so it's 54 centimeters wide. That means we have to, so we have pi we need our radius, so that's 54 divided by 2 squared times by the height, which is 64.8 centimeters. So our value will be in centimeters cubed, which is annoying because we need it in liters. So let's see, does this have pi? Oh yeah, great. Pi times the radius, which is 54 divided by 2, that's the radius, squared, times the height, which is 64.8. This is the volume in centimeters cubed. But we need it in milliliters. Oh, so we need it in, so 148,406 centimeters cubed. 1 centimeter cubed is the same as 1 milliliter. That's true. So we can just say, okay, well, it's actually in milliliters. Well, we actually want this in liters. So how do we convert this to liters? So let's see. So 1,000 milliliters for 1 liter. So we're going to divide by 1,000. So I'm just going to do the decimal. 1, 2, 3. 148.406 liters. Okay, great. So we have our volume now after a lot of effort. Okay, what else are they giving us? The maximum safe pressure is 4.2 megapascals. Great. We have our pressure, but it's not in atmospheres, so we have to convert that to atmospheres. This is the worst problem in all of ALEX. So if you can do this one, then you're set. Okay, so we have megapascals. Mega is times 10 to the 6. And Alex gives me a conversion for pascals to atmospheres. So, okay, I'm going to just make this 101,325 is pascals. So if I multiply this by 101,3, yes. I'm just going to convert it to pascals. 101,325 pascals. So I have my decimals here. I just made my decimal for 1 atmosphere. Oh, they don't have atmospheres. Great. So let's go back here. 4.2 times 10 to the, do I have that button? 6 divided by, oh, I should put this in parentheses. This is I think I counted one time and it's like a 6-step problem. So I convinced them not to put it on the final, but I didn't convince them to not take it off of our ALEX homework. So this is now in atmospheres. 41.45 atmospheres. Okay, great. So now we have pressure. We have our volume. We have our pressure. They're trying to give us moles. This is grams. So our mass is 14.1 kilograms of sulfur hexafluoride. So what's the formula? It's telling us sulfur. How many fluorides? 6. So first I'm going to put this in grams. So I'm going to times by 1,000. So 14,100 grams of sulfur hexafluoride. I need this in moles, so I have to find the molar mass. So I'm going to go to my Alex table. Sulfur. Is it going to let me type? Plus, yes, 6 times, oh, did I do that? Hexafluoride times, oops, I didn't do that right. Plus 6 times, there we go, fluorine. Okay, so sulfur plus 6 times fluorine gives me the molar mass. So I'm gonna, from grams to moles, I need to divide by that molar mass. So I'm just gonna put, let's copy this. 1,400 and 100 divided by the molar mass. So this is how many moles. This is annoying because there's so many steps. If you mess up one of them, you don't know where you're messing up. Okay, so this should be our moles of, that's N. We just found N. Moles of the compound. And we have R. R is a constant. R is 0.08 something from last time. I don't remember. 1, 3, 1.
0.082.
Things. And then it has our units. Okay, so we are looking for, what is it asking for? Calculate the maximum operating temperature. We're looking for temperature. So if we go back to our equation, we just found pressure, volume, moles. We have the gas constant. We're looking for temperature. So if we divide both of these sides by NR, then we'll get T. So T is equal to that pressure that we found times the volume divided by the number of moles times the gas constant. Okay, so let's try to type that in. So pressure, what was our pressure? I have my pressure is 41 point. I'm going to keep as many decimal points as I wrote down. Probably should have kept a few more. Pressure in atmospheres times volume in liters, 148.406. This is I feel like this is like, I took some engineering classes and this is like engineering, which is good, but I feel like this is a chemistry class and we're not doing this. Anyways, this problem bothers me. So if you get this one and you get stuck, come talk to me and we can get through it. 5, 4, 2, 6 times by the gas constant, and that one we can look up. Gas constant in the right units, liters, atmospheres, moles, Kelvin. Okay, so this is my temperature. It is in Kelvin. And they're asking for it in Celsius. So we have to subtract off 273.15. Okay, so that's my temperature in Celsius. I think. Yes, I think I went the right way. 503. Okay, and it might be wrong because we did so many steps. If we miss one thing, then the whole thing gets wrong. Okay, great. Okay, so now we are out of time. If you have questions on this one is the most annoying in all of Alex. So let me know if you need help with this one. Okay, so there's lots of versions of this problem. So make sure that you can do all of them. I think this one does show up on the test. This one won't show up on the final. Okay, we'll keep working on. If you come on Wednesday, you can, if you need to finish the lab, you can finish the lab, or you can work on Alex. We won't do any instruction on Wednesday.
I hear a question for tomorrow.
Yes. Mm-hmm. Yes, baby.